In this video, we're going to learn about KSP ice charts, or also referred to as solubility equilibriums. So what I would like for you to do, just take a moment, read over this intro information. So hit pause and come back after you've read over this. So insoluble salts are actually slightly soluble. So when we say we have lead iodide, for example, lead iodide is insoluble in water. It precipitates out of solution. Technically, a very small amount of it dissolves into lead ions and iodide ions in aqueous solution. So when we take lead iodide, which we know as to be insoluble, and we dump it into water, a very small amount of that insoluble solid actually dissolves. So all these solubility rules that we have been talking about doesn't mean that none of it dissolves, but actually just a tiny bit of it is going to dissolve. So once the solid starts to dissolve, it's going to form those aqueous ions, and equilibrium is going to be established between the solid and the dissolved aqueous ions. And remember, equilibrium means the rate of the forward process or reaction equals the rate of the reverse. And so you're going to form a dynamic equilibrium between that solid and those aqueous ions. And once equilibrium is established, we've created a saturated solution. In this video lesson, we're going to focus in on two of the four main types of KSP problems. We're going to focus in on number 1 and number 2. We're going to learn how to create KSP ice charts and calculate something called the molar solubility, which represents the amount of solid that is actually dissolving into ions. And from our ice chart, molar solubility is X. And then we're going to learn how to solve for KSP values using molar solubility values. So let's take a look at problem number 1 on your paper. Problem number 1, we have silver chloride. It dissolves in water according to this equation here, and it has a KSP value of 1.8 times 10 to the negative 10. KSP is that equilibrium constant. This one is known as the equilibrium constant solubility product because we're dealing with solubility problems, the solubility of solids or slightly soluble solids in water or solutions. Notice that this KSP value is 10 to the negative 10. That's very, very, very small. And that's why typically we just say, oh, silver chloride is insoluble, none of it dissolves, because the KSP value is so small, really barely any of it dissolves, but technically a little bit of it is dissolving, and that's what we're going to calculate in this problem. So first off, we want to write the KSP expression for the dissolution of the silver chloride solid in water. KSP expressions follow the same format as KC and KP expressions. It is products over reactants using coefficients as the exponents, only including aqueous compounds and gases. In solubility problems, we don't have gases. We're only going to have aqueous ions and solids or liquids. So here we go to our products. First product is aqueous ion of silver. So it goes square brackets, silver ion. Its coefficient is 1, so its exponent is 1. Chloride aqueous ion. Its coefficient is 1, so its exponent is 1. And over our reactants, but our reactant is a solid, so there is no denominator here. And there is never denominators for KSP expressions. And that is because in KSP expressions, the reactant is always a solid. So we know solids do not go into K expressions. There will never be denominators in a KSP expression. Part B, they would like for us to calculate the molar solubility of the silver chloride in water. Molar solubility, remember that means solve for X from an ice chart. So we're going to start by writing our equation. So we have our reaction. I stands for initial. So we have some amount of silver chloride being put into water. The real amount doesn't matter because this is a solid. It's not going to appear in our calculations. The starting concentration of silver ion in water is 0. Same thing for the chloride ions. There's 0. There's nothing in water but water molecules. And for the change, we know we're going to shift towards the product side because we have 0 products. So we're going to minus X from our reactant plus 1X for the silver plus 1X for the chloride. And the equilibrium is the sum of the initial and the change rows. So you're going to have some amount here for your solid, X, and X for your products. And you can separate here just to make it a little bit easier to see. And you have your complete ice chart. Now, remember, solids do not appear in our KSP expression. So essentially, we can ignore that entire reactant column for KSP ice charts. They're not important because they're solids. So we want to solve for X from this ice chart because X is going to be molar solubility. Well, I know the KSP expression from part A reads the equilibrium concentration of silver ion times the equilibrium concentration of the chloride ion. And according to your ice chart, both of those are X at equilibrium. So we're going to set up our KSP expression in terms of X. We're going to substitute in X for the silver, substitute in X for the chloride. So KSP equals X squared. And they gave us the KSP expression, or I'm sorry, the KSP value. It is 1.8 times 10 to the negative 10. Set that equal to X squared and solve for X. X equals 1.3 times 10 to the negative 5 molar, or you can write that as moles per liter. That is your molar solubility. It tells you how many moles of silver chloride are dissolving for every 1 liter of water. Okay, problem number 2, we have the KSP value of calcium fluoride. It's 4.0 times 10 to the negative 11. Again, very small KSP value. That means this is heavily reactant favor, heavily favors a side with the solid precipitate. They're asking us to calculate the molar solubility of calcium fluoride in each of the following. So again, we are solving for X from one of our ice charts. So first start by writing out the equation. You have solid calcium fluoride. It's going to dissociate into calcium 2+ aqueous ions and fluoride negative aqueous ions. Its coefficient for fluoride is 2 because its subscript in calcium fluoride is 2. So watch out for that stoich right there. Make sure it is conserved. So we're taking some amount of calcium fluoride, doesn't matter the quantity, and we're dumping it into a beaker of water. So initially, the concentration of your aqueous ions is going to be 0. The change you minus from the reactant side, you add to the product side. But when you get to the fluoride, remember, bring down that coefficient of 2. So at equilibrium, you're going to have some amount of calcium fluoride, X amount of calcium ion, and 2X amount of fluoride ion. And they would like for us to calculate the molar solubility once this equilibrium is established. Essentially, you are solving for X because X represents the quantity of calcium fluoride that is undergoing this change. It is X from our ice chart. So we're going to set up our KSP expression first of all. KSP equals calcium 2+ ion to the first, fluoride negative ion squared because its coefficient is 2. And this is a KSP expression, so there is never a denominator because our reactant is a solid. I'm going to plug in the KSP value of 4.0 times 10 to the negative 11. And then our equilibrium concentrations of calcium ions and fluoride ions from our ice chart. So at equilibrium, calcium is X, fluoride is 2X, and that quantity is being squared. So to simplify this, you get X times 2X squared, that's going to be 4X squared, and then times X. So KSP equals 4X cubed. Set that equal to 4 times 10 to the negative 11 and solve for X. So divide both sides by 4. You get 1 times 10 to the negative 11 is equal to X cubed. And take the cube root of both sides, and that will give you X. Just as a refresher, to get the cube root button on your calculator, hit Math 4, and that will bring up the cube root option. And so the cube root of 1 times 10 to the negative 11 is 2.2 times 10 to the negative 4. That is equal to X, and the unit on X is a capital M, or you can write it as moles over liters. Those mean the same thing. So the molar solubility of calcium fluoride in pure water is 2.2 times 10 to the negative 4 molar. Part B. Now we want to calculate the molar solubility of sodium fluoride. The molar solubility of calcium fluoride when it's not put into water anymore, but placed into an aqueous solution of sodium fluoride. So that means there's already some sodium ions present in the solution and fluoride ions present in solution before I add the calcium fluoride to it. So we're going to rewrite our equation. So calcium fluoride, solid, breaks up into calcium 2+ aqueous and 2 fluoride aqueous ions. There's some amount of calcium fluoride being thrown in. Again, doesn't matter because it's a solid. Now, this is being put into a solution of sodium fluoride. So the initial concentration of calcium is still 0, but the initial concentration of fluoride ion is 0.20 molar. And I'm getting that from the problem itself. It's 0.025 molar fluoride ions. So there's already some fluoride ions in solution before we even add in the calcium fluoride. And let's just chat for a moment. How do you think having fluoride ions already present in the water is going to affect the solubility of the calcium fluoride? Well, think of this kind of as Le Chatelier's principle. If there's already some product present, how is this going to affect the equilibrium? It's not going to push it forward as much because there's already some product present. So we would expect the solubility of this compound to decrease when there is already some of the dissolved ions in solution. But let's calculate and see for sure. Let's see, minus X plus 2X. So there's some, really, I don't even care. I don't even have to do that solid column. It's irrelevant. Calcium 2+ is X. Now when I get to fluoride, it's 0.025 molar plus 2X. And since KSP values are typically so small and X is so small, if I was to solve for X and then plug it in to my equilibrium concentration for fluoride, its concentration is not going to significantly change because X is going to be so small. And when I plug it in here, it's not going to significantly change the 0.025 molar. So you are allowed to approximate for KSP ice charts you're allowed to say that the equilibrium concentration of the fluoride is still 0.025 molar. So we're going to write out our KSP expression. We know the value of KSP is 4 times 10 to the negative 11. Calcium is X. Fluoride, however, is 0.025 molar, and that is squared, and solve for X. X equals 6.4 times 10 to the negative 8 molar. And let's compare that to our answer from part A. In part A, in pure water, when calcium fluoride dissolves in pure water, it has a molar solubility of 2.2 times 10 to the negative 4. And then now, in 0.025 molar sodium fluoride, it has a molar solubility of 6.4 times 10 to the negative 8. This is way smaller. So calcium fluoride is less soluble in the sodium fluoride solution than in pure water. And that's because the sodium fluoride solution already contains some of this fluoride ion. This is known as the common ion effect. So when you're taking a salt and you're dissolving it in a solution that already contains one of the ions that salt is going to break up into, the presence of that ion decreases how much of the solid salt can dissolve. So it decreases the value of X, which is your molar solubility. Okay, for part C, we're going to calculate the solubility in grams per liter in the solution from part B. So part B, X is in terms of moles per liter, and they would like for us to convert the moles per liter into grams per liter. Okay, so 6.4 times 10 to the negative 8 molar. Think of molar not as capital M anymore, but moles of calcium fluoride that dissolve in every 1 liter. And the problem would like for us to convert this into grams per liter. So we can do a little dimensional analysis. For every 1 mole of calcium fluoride, the molar mass is 78.08 grams. Moles, calcium fluoride cancel, and you're going to be left with grams of calcium fluoride divided by liters. And I get 5.0 times 10 to the negative 6 grams per liters. For number 3, now we have iron 2 hydroxide. They gave us the KSP value. They would like for us to calculate the molar solubility of the iron hydroxide in each one of these 3 cases. So I want you to hit pause, and I want you to try these on your own, and then come back and check your answers. Okay, you should have attempted number 3 on your own. Now for part A, you're calculating molar solubility when iron hydroxide is put into pure water. So your initial concentrations of the 2 aqueous ions is 0. You solve for X, and you get a value of 5.8 times 10 to the negative 6 molar. Feel free to hit pause and check your work. Part B, now you're dissolving the iron hydroxide in an iron nitrate solution, which has a starting molarity of 0.010 molar. So here's your ice chart for letter B. And when you calculate X, you'll notice that X is 1.4 times 10 to the negative 7 molar, and this is known as the common ion effect. Having the iron already present in the solution lowers the solubility. Part C, we're taking iron hydroxide and now dissolving it in a solution already containing hydroxide ions. So the initial hydroxide ion concentration is 0.020, so that means its equilibrium concentration is also 0.020 molar. And now X, your molar solubility, equals 2.0 times 10 to the negative 12 molar. Again, that common ion reduces the solubility of the solid.